Good morning. We're continuing with the gas laws that we started talking about earlier. So we're going to be talking about Charles' law today. You'll notice that one major difference with Charles' law from Boyle's law is that Charles' law is a direct proportion. So Charles' law states that the volume of a given mass of gas is directly proportional to its Kelvin temperature. All right, and at constant pressure. So what that means is that pressure will not be included in our problem, or it will give us the same pressure twice, or it will tell us again that pressure is constant, meaning that we will not have to include it in our equation. You'll notice that our equation does not include pressure. We only have volume and temperature. This part about Kelvin is very important. You must include only Kelvin temperatures when you go to solve your equation. I want to go back for just 1 second to directly proportional. If you remember from Boyle's law, Boyle's law was indirectly proportional or inversely proportional, which meant as one variable went up, the other one went down. Now we have a direct proportion, which is why volume and temperature are being divided. So what that means is that as one variable increases, the other variable is going to increase. So if we were to graph it, it would look like this. That's another way we can check our answers. If it says in the problem that temperature increases over time, we can check our answer and make sure that the volume increases. Or if the problem is changing volume and decreasing volume and asking for temperature, then the temperature should also decrease. Okay, let's talk about this Kelvin temperature real fast. In your reference packet, it gives you, just going to show you real fast, standard temperature, 0 degrees Celsius or 273 Kelvin. So what that means is if they give you degrees Celsius, in order to get Kelvin, you have to add 273. So for example, if I had 25 degrees Celsius, I would add 273 to get 298 Kelvin. All right, so given all of this information, we're going to go ahead and jump into a problem. All right. So this problem states that a balloon filled with helium at 55 degrees Celsius occupies 3.5 liters. If the temperature decreases to 35 degrees Celsius, what volume will it occupy? So when I do these problems, it's a great idea to go ahead and underline or write down all of the variables that you have. We're going to be learning several gas laws that have lots of variables. So if you write down the variables that you have when you go to figure out what kind of problem you'll be doing, you'll understand it a little bit better. Let me show you what I mean by that. All right, so it says I have a balloon filled with helium at 55 degrees Celsius. Well, 55 degrees Celsius is a temperature. Okay? The next thing that my problem has says it occupies 3.5 liters. 3.5 liters is a volume. It says if the temperature decreases to 35 degrees Celsius, what volume will it occupy? So now I know that I'm looking for a volume. I'm not given any other variables. So given this information, I can pretty well figure that I am doing a Charles Law problem. So I can set up my equation, V1 over T1 equals V2 over T2. Alright, before I go to solve this equation, remember from the last slide, I have to have Kelvin instead of Celsius. So I'm going to add 273 to both of these. Alright. Alright, so 55 plus 273 is 328. 35 plus 273 is 308. And make sure you include that that is Kelvin, so we know when we go back to check that we have converted to Kelvin and we've done the problem correctly. Alright, we're solving for volume. And I didn't do this at the beginning. We should have made sure that we have volume 1 and volume 2 set up. Alright, as the problem reads, it says a balloon filled with helium at 55 degrees Celsius occupies 3.5 liters. Alright, and then it says the temperature decreases. So that's what it's going to be changing to. And it wants to know at that 35 degrees that it's changing to, so that final temperature, what volume will it occupy? So that's going to be my T2 and my V2. This initial temperature and volume are my T1 and my V1. Alright, so I'm solving for V2. In order to get my V2 by itself, I can multiply both sides by T2. Remember, when I do this, I'm just rearranging the equation. Okay? And I can rewrite my equation to get V1 multiplied by T2 over T1. Then I can plug everything into this new equation. This is one place where I see people mess up the most often. I'm going to plug in my V1. V1 is the only volume we have right now. So I'm going to plug in my 3.5 liters. But then T2. Make sure you are plugging in T2. It's written on top. It's the first temperature that we're going to plug in. But make sure that you are plugging in T2 and not T1. Okay? With all of these equations that are like this, make sure that you are plugging in the proper variable. And that's one of the reasons that I rearrange the equation as opposed to plugging my variables first. Alright, so I have 308 Kelvin divided by, and my T1 is 328 Kelvin. Before I move on, I'm going to make sure that my variables cancel, and I'll be left with, not my variables, my units cancel, and I'll be left with a unit that works for the variable that I'm solving for. So, I'm solving for volume, so I should end up with a volume unit, which is liters. So my Kelvin should cancel, and it does. I have Kelvin divided by Kelvin. I should be left with liters. There's no liters on the bottom, so I am left with liters. Now I can plug this into my calculator. I have 3.5 multiplied by 308 divided by 328. And I get 3.286. So I'm going to round that to 3.29. really, again, liters. All right. We're going to move on to a slightly harder problem. A gas at 359 Kelvin occupies a volume of 0.7 liters. At what Kelvin temperature will the volume increase to 1.12 liters? All right, so just like my last problem, I'm going to write down all of the variables that I'm given. So it says 359 Kelvin. Okay, so I'm given, remember Kelvin is the temperature. Occupies a volume, so it tells me that it's volume, 0.7 liters. And then it says, at what Kelvin temperature will the volume increase? So that's going to be when it's increasing, it's telling me that it's changing over time. So that is going to be my V2. 1.12 liters. So I know that my T2, it wants to know what the temperature at the 1.12 liters is going to be. So that is going to be my question mark. And these are going to be my T1 and my V1. All right, I do not need to convert my temperature because it's already given in Kelvin. Okay, so we can go ahead and check out which equation we think we're going to be using. I'm only given volume and temperature. I don't have pressure. I can assume that pressure is constant. So I'm going to set up my formula. V1 over T1 equals V2 over T2. And I'm solving for T2. So sometimes these problems can get a little hairy. I'm going to show you how to do this. I'm going to show you two ways of doing this. You can pick which way you like to do this. All right. So since I'm solving for T2, right now it's on the bottom of the equation. I can't keep it on the bottom. So basically what I need is I need to have T2 on the top. I need to have T2 equals some stuff. Okay? So I can't have T2 on the bottom. All right. So my first step needs to be to get T2 onto the top. The way that I'm going to do that is to multiply by T2. That will get T2 onto the top. Whatever I do to one side, I have to do to the other. T2 on this side will cancel. And I'll be left with T2 times V1 over T1 equals V2. You might be asking right now, not solving for V2, got V2. But remember, my goal was to get T2 on the top, okay? So now I can solve for T2 more easily. How do I do that? Well, I multiply by the inverse, which means basically I'm going to flip these. So I'm going to multiply by T1 over V1. And remember, whatever I do to one side, I have to do to the other. So T1 cancels, V1 cancels. So I'm left with T2 on this side, and it's the only thing. So I'm going to end up with T2 equals, just like my goal was. T2 equals V2 times T1 over V1. Okay, now I told you that I was going to give you two ways to solve this. So another way is, and you might have thought that this was getting a little bit hairy. So this next way is called cross multiplication. Oops. So cross multiplication means that you are going to take the variables that are diagonal from one another and multiply them. So I'm going to take V2 and multiply by T2. Notice T2 is now going to be on the top of the equation. And then I'm going to do the same thing to my other two variables, T1 times V2. Alright. Now remember, my goal ultimately is to get T2 on the top, to get T2 by itself. So how do I get T2 by itself? Now I have to divide both sides by V1. Now I'll have T2 is equal to this side. I'll rewrite, oops. So notice that no matter which way I choose to solve using my variables or to rearrange my equation, I still get the right equation. So now I can use my newly rearranged equation to solve for T2. So I'm going to, just for simplicity purposes, erase all of my work so that you can see what I'm doing a little bit better. So remember, I rearranged my equation. So now I have T2 is equal to V1, V2. Make sure you rewrite your equation correctly. V2 times T1 over V1. And now I can just plug everything in. Again, making sure that you plug everything into the proper locations. V2 is 1.12 liters multiplied by T1, which is the only temperature we have, 359 Kelvin, divided by my V1, it's 0.7 liters. Alright, before we solve using variables, before we solve this equation, I want to make sure of a couple things. Will we be left with the unit that I want? Meaning, do these liters cancel? And will I be left with a temperature unit? Yes, I'll be left with Kelvin. Second thing I want to make sure of. Let's look back to our problem. It says, at what Kelvin temperature will the volume increase? So let's think back to what volume and temperature do in my proportion. They are directly proportional to one another. Meaning, as temperature increases, volume increases. Or as volume increases, temperature increases. So when I go to solve this problem, my temperature should be bigger than it was initially. So it should be bigger than 359 Kelvin. So we're going to solve, and our check is going to be to make sure that that number is bigger than 359. And I get 574.4. I would say that is definitely bigger than 359 Kelvin. My units are Kelvin because the liters canceled and I'm left with Kelvin. And that is it for Charles' Law.